Have you ever wondered, what are we really made of? Scientists have been searching for the most fundamental building blocks of our world for thousands of years. The ancient Greeks first thought that earth, wind, fire, and water were the elemental properties of matter. Centuries later, we discovered cells, then molecules and the atomic elements. But did you know that there are even smaller particles making up the protons and neutrons inside of atoms? These minuscule particles are called quarks and gluons, and they make up everything that we see around us. Allow me to set the stage for these tiny players. If we wanted to see a quark, we would need a microscope with a magnification of more than 1 trillion, far beyond the limitations of this technology. So how can we see what's inside a proton? The only tool on Earth that's powerful enough for us to study quarks is a particle collider. These particles are accelerated to nearly the speed of light, and only at this energy scale can we break open protons to reveal the mysteries of matter. In fact, with this amount of energy, we're actually recreating an early state of the universe just after the Big Bang, called the quark-gluon plasma, when the quarks and gluons were the only particles in existence. No atoms, no molecules, no planets, stars, or galaxies, just these fundamental particles filling our universe. In my research, I want to know how the ordinary matter that we see around us evolved from the Big Bang. I search for those answers by studying what happens at particle colliders. After the collision of two nuclei, after the quark-gluon plasma phase when the system has cooled, a whole zoo of particles flies into the detector. What you see here is an actual picture of the aftermath of one of these collisions, where each colored line is a particle moving through the detector. What we find after these collision events are new, exotic particles that contain a different, heavier type of quarks than those in the protons and neutrons. Because these quarks were so peculiar, they were given the name strange quarks. Part of my research is characterizing these particles, and what I have found is that they have different properties due to the presence of these strange quarks. The state-of-the-art models that I use in my research allow me to tease out and separate particles containing different quarks. I have found that these strange quarks exist at higher temperatures than ordinary quarks. This leads to what we have coined the quark species hierarchy. This hypothesis of higher temperatures for heavier quarks connects back to the early universe. We have evidence that these heavier quarks would have been created at earlier times, and this means that it might still be possible to find clumps of this exotic matter left behind as remnants of the Big Bang. This has an important impact on the fields of astronomy and astrophysics, since this primordial matter could be the key to what lies at the core of very dense celestial bodies like neutron stars. In addition to explaining the origins of matter, understanding the properties of this uncharted microscopic realm also enable us to develop new, groundbreaking technologies, like how the discovery of electricity allowed us to develop computers, including the one you're using to watch this video. Thank you.